Today, we're diving into a story where some of the most abstract laws of physics, the invisible dance of atoms, had devastating real-world consequences for a community. It's a story about a threat you can't see, you can't smell, you can't taste, but it was hidden in the very land and even the homes people lived in. This sentence? Wow, it just gets right to the heart of the matter, doesn't it? The needs of a single generation created a toxic legacy that will be around for, well, pretty much forever on a human timescale. This isn't just a history lesson, it's a problem that stretches into a future so deep it's hard to even wrap your head around.
So, how did all this begin? Well, it didn't start in a lab. It started on the world stage, right at the dawn of the atomic age. The Cold War created this absolutely insatiable demand for one specific element, uranium.
Yeah, the uranium rush was incredibly fast and intense. For a few decades, this land was heavily mined for a very specific, rare type of uranium, U-235. That's the stuff you need for nuclear weapons and power plants. But here's the catch. For every little bit of U-235 you get, you're left with huge amounts of U-238. And that leftover rock was just piled up, creating this massive, ticking time bomb that eventually led to catastrophes like the Church Rock disaster in '79. Okay, so let's zoom in. Way in. Let's go from that huge, sweeping landscape right down to the atomic level. Because to really get what's going on, you have to understand the weapon. And in this story, the weapon is a particle so tiny, it's literally invisible. The main source of the harm here is something called an alpha particle. The best way to think of it is like a tiny, super high-energy cannonball. It gets shot out from the nucleus of a decaying atom. It's heavy, it's powerful, but it can't travel very far at all. And that, it turns out, is its most fascinating weakness. And here is the central, mind-bending paradox of this whole thing. If that alpha particle hits you from the outside, it's totally harmless. It can't even get through the top layer of dead skin cells. But if the atom that fires that particle gets inside your body, if you breathe it in or ingest it, that's a whole different story. That tiny cannonball is now firing from point-blank range, smashing directly into living cells and shredding your DNA. So you see, the real danger isn't being near the source, it's getting the source inside you. So you might be wondering, how does a solid rock get inside your lungs? Well, it happens through this process called a decay chain. The uranium in those waste piles doesn't just sit there, it's slowly turning into other elements. One of those is radium, which then decays into radon. And radon is the key. Why? Because it's a gas. It doesn't stay put in the rock. It can seep up through the ground, fill a house silently and invisibly, and then it's just inhaled. So once that radioactive material is inside, something even more treacherous happens. Our bodies don't just fail to see the danger. In a tragic case of mistaken identity at the molecular level, our bodies can actually welcome this poison in. The mechanism behind this is called molecular mimicry. It's a fancy term, but the idea is simple. It's when a harmful substance is such a perfect chemical counterfeit of a vital nutrient that our own biological systems get tricked. They can't tell the difference, so they absorb it and try to put it to use. Now, take a look at this. This chart shows you exactly how that counterfeit works. See radium? Down there at the bottom? Now look right above it. There's calcium. Because they sit in the same column on the periodic table, group 2, they have really similar chemical properties. So, to our cells, which are constantly on the lookout for calcium to build strong bones, radium looks close enough to be the real deal. And the consequence of that mistake is absolutely devastating. The body thinks it's calcium, so it actively grabs this radium and takes it right to our bones, building it directly into the bone matrix. That's why this stuff is called a bone seeker. It doesn't just pass through your system. It becomes a literal part of your skeleton, sitting right next to your bone marrow, the very place your body produces blood cells. Okay, so we've seen how this stuff gets inside the body. Now let's get to the core of it, the fundamental physics that explain why this situation turned from a hazard into a full-blown catastrophe for the people living there. All right, this right here is probably the most important rule in radiation safety. It's called the inverse square law. It's a simple but incredibly powerful idea. The farther you get from a source of radiation, the safer you are. But it's not a steady drop-off. If you double your distance, your exposure gets cut down to just 1/4 of what it was. Triple the distance, it drops to 1/9. Simply put, distance is your absolute best friend. So, what happens to that all-important inverse square law when your distance from the source is 0? That's the tragic heart of this story. For many Navajo families, those piles of rock from the mines were seen as free building material. They were used to build the foundations and walls of their homes. The source of radiation wasn't miles away. It wasn't even across the street. It was the floor they slept on. The distance was zero. The second critical piece of the physics here is time. See, radiation damage adds up. It's cumulative. A dose that's so tiny it's basically harmless on any given day doesn't just vanish. It builds. Day after day, year after year, living in that environment, that chronic, low-level exposure accumulates into a massive, life-threatening total dose. This all brings us to the guiding principle of radiation safety, a concept called ALARA. It stands for as low as reasonably achievable. And you do it with 3 basic tools. Limit your time near a source, maximize your distance from it, and use shielding. But for the families living in these homes, every single one of those rules was turned on its head. Their time was constant, 24/7. Their distance was 0. And the very shielding meant to protect them from the elements was the source of the danger. So we've looked at the history, the biology, and the physics, but to really feel the true weight of this legacy, we have to talk about the time scale. And honestly, it's a scale that's almost impossible for our brains to comprehend. The concept that governs this is called half-life. You can think of it as the universe's own atomic clock. It's the amount of time it takes for half of a chunk of radioactive atoms to decay into something else. And the most important thing to know about it is that this rate is a constant of nature. You can't speed it up, you can't slow it down, it just is. The half-life of uranium-238, the main stuff left in those waste piles, is 4.5 billion years. To put that into perspective, that is roughly the age of the planet Earth itself. The hazard left behind from just a few decades of mining will, for all practical purposes, last forever.
This leads to a profound and fascinating challenge. How do you warn future generations about a danger that will outlast our civilization, our languages, even our symbols? This quote is actually part of a proposed message designed by scientists trying to solve exactly that. They're trying to communicate danger by completely negating any sense of value, hoping to repel any future explorers instead of attracting them. And that's really the question that we're left with. It's a whole field of study called nuclear semiotics, the science of creating warnings that last for millennia. It forces us to think beyond just cleaning up the past. It forces us to think about our duty as ancestors to a future so deep we can barely imagine it. How do you write a keep out sign that lasts for 10,000 years? That is the final haunting challenge of this invisible harm.